so let's get started. So, a couple of things. So, I think today will be our last lecture on transaction, and that will cover pretty much everything I wanted to cover for this class. And next week, the good news is we are ahead of schedule. And next week, when we come back we lose one lecture due to the Thanksgiving holiday. But next week, we do have another week. Then it's the final week, right? I think we have 2 weeks.
Yeah.
2 weeks. That'll give us actually 4 lectures. That's really great news. Because I'm going to use those lectures to cover things like NoSQL systems, in-memory databases, and some of the latest development in the space of large-scale data management. But the bottom line is, keep this in mind. After going through the relational kernel, you guys should feel very comfortable in using or understanding the design and the implementation of any other data management system like NoSQL and things like that. Of course, there are some challenges over there, which is how do you scale out to a cluster rather than using a single node setup as we discussed here. And those are some of the topics I plan to cover in the remaining 4 lectures. One thing to note is that the final test will be up to whatever we cover today. So the next 4 lectures will be really just FYI for your information kind of lectures. So really just enjoy the lecture time, and you don't have to worry about preparing for the final exam on those 4 lectures. Okay. That being said, as I mentioned before, the final test basically will cover everything in the scope of written assignment 1 to 4. So you turn in written assignment 3 last week. I released the solution last night. I will go over that solution really quickly today. And I also released written assignment 4 right here, which is on transaction basically. Everything about transaction here. Start with locking, concurrency control, all the way to crash recovery that we will be covering up today. I also released Lab 5 today, which is on transactions. But Lab 5, actually we have 2 labs for transactions, but I will only release part of it. The second part, we will not ask you to work on it, given how tight the schedule is. So the first part of the transaction lab is on concurrency control. So it doesn't really cover crash recovery that we will be discussing today. Okay? So in my opinion, this is a fairly easy lab. Because once you understand what straight two-phase locking is, once you understand how Log Manager works, which my PT student had discussed with you on last Thursday lecture, you should be able to do this without much trouble. Okay? You should be able to do this lab without much trouble. Okay? Now, yeah.
You wrote the 8. That's pretty tight because you said the homework you're on the 6th.
Yes. So this deadline is negotiable. Okay, in the sense that the final test is on the 12th. So we can either have the lab turn on the 8th, or we can have the lab turn even after the final exam. I'm okay with that, as long as you guys are okay with it. The reason I set the deadline to the 8th is that I don't want you to worry about working on a project in your final week. So we will set December 8th for now. That's the target. If you have trouble making that deadline, just let me know. The last one, I'm very flexible, given how tight the schedule is. I'm very flexible in considering giving you extension if needed. For the last lab only, okay? There's no extension for homework 4 and lab 4. There will be no negotiation for that. But for lab 5, yes, I'm open for negotiation. If you think you need more time for lab 5, that's totally understandable. Just let me know. Okay? All right. So now let's look at homework 3 solution. Homework 3 is about query evaluation and query optimization. The first one is a test on merge sort, and in particular it's a 2-way sort. So it's very 2-way merge sort. So it's very straightforward. And then here, he asks you about some optimizations. So remember the optimization, refresh your memory again. What is the optimization we talk about for merge sort? Well, the idea is you can, when this condition holds, you can actually do just linear I/O. Right? We talk about the optimization for the merge sort, right? So that's what this calculation is about. It's fairly straightforward, I think. The question 2 asks you about how to generate a particular query plan, right? So in this case, is it too small? Is it better now? So in particular, this one, the only thing we're doing here is you want to kind of push down the selection operator, like you do here, okay? And of course, another option is for you to push down the projection operator as well. It's possible if you do that. But remember, if you do push down the projection operator, you need to put out not only the projection attribute, but also those attributes needed for the join operator. That's the only kind of variation you may have. And for problem number 3, it basically asks you to evaluate this query with regard to different join algorithms. So to set up your solution, you want to calculate these numbers first. Number of pages in S, number of pages in R, and number of pages in the buffer. In this particular setup, I gave you this value directly. I never give you the value of n or b, but I give you the value of n over b directly. I also give you the value of n over b directly. I never give you exactly the value of n or b. I just simply give you the value of n over b, right? So keep that in mind. And the calculation is fairly straightforward if you know all these algorithms. So I will skip all these solutions. You can look at yourself. If you have any questions, I will be happy to answer those either in my office hour or via email. Okay. Problem 4 is on selective estimation. It's basically on curve optimization, right? Remember, on curve optimization, unless otherwise specified, if there is no histogram provided to you, you will assume simply a uniform distribution. That's essentially the gist of the problem, right? So, and you also assume when there are multiple selection predicates, you also assume independence among those selection predicates, unless otherwise specified. So that means that this problem becomes fairly easy. You, using the notion of uniform distribution, you can derive the selectivity for each of these query predicates. And using the notion that they are independent, you can multiply the selectivity of different terms together, and then get an estimation for the final output. Okay. And then I ask you for left deep tree plan. These are all the possible left deep tree plans. And then it asks you some, again, similar to question 3, asks you different order of join and different algorithm for the join operator. What is the cost in each particular combination? It's fairly straightforward, if you ask me. Okay. So the last problem, I will spend some time here to work through the proof with you. So the last problem, in class, we talk about selective estimation using histogram. But I also mentioned another very common technique people use for selective estimation is sampling, is to use random sampling. Okay? So, and this last problem really is designed for you to understand the concept of sampling. Okay? So the basic idea of sampling is, for example, if I want to estimate the average GPA of all students in my daily class. Okay? One way to do that is to ask each of you what's your GPA value. And I ask each of you for like 40 or 45 times. We have 40 or 45 students. We add up the value and divide by 40 or 45, whatever the number is. But this could be expensive, right? For 40 or 45 students, that's okay. But if you want to calculate the average whatever income for US population, that's 300 million or 400 million queries you have to do. That's very expensive. So one effective way of doing that is to use sampling, right? So instead of ask each of you, I randomly select a few of you, then ask what's your GPA value. The key here is you have to ensure randomness. You have to ensure randomness. For example, I cannot just ask only students from this side. Maybe there is a bias in how you choose your seat. All the good students tend to sit on the left-hand side. Just what I'm saying. I'm not saying that's the case, right? So if you only ask for choose your sample from this side, you will get a really biased estimator, right? So you really want to make sure the elements you have chosen from the population is a good representation of the population. The one way to do that is to do random sample. So random sample. So random sample means the following. Okay, first of all, you need to specify what's your population. Right? This is the one thing you need to specify. Secondly, what's your sampling rate? Typically, no matter go, that's from 0 to 1. From 0 to 1. And what that says is any population, let's say population, this is the X, is a set. Right? This is the set. And you also need to define the attribute of interest, right? Or in other words, the domain for the elements in X. Let's say any X from capital X, they're from a universe U. They're from a universe U. That's essentially the domain, right? That's the domain. For example, all human beings, X is limited to US population. Right? So that's the difference of the two. Now, once you have a sampling rate goal, what that says is you're going to draw a sample that's called S. S is the set. That's a subset of capital X. So S is the set. When I say a random sample, so a random sample doesn't mean just a single sample. It means a set of samples. A random sample is a set of samples. From X, such that for any element X, small x, from the capital set X, what's the probability X is in S? Well, this probability must be, what's the probability? Must equal to your sampling rate, which is what? You want me? Simple, very simple argument, right? But furthermore, for any xy, must equal to rho squared. Means they're independent. Means they're independent. And this can continue on. If it's x by z, this must be rho to the cube. And this continue to all the way to the entire set of S. So it's total independence. Okay? It has total independence. So that's the definition of random sample, right? However, you may have, given this setup, obviously you can have many different random samples. Many different choices you can make, right? How many possible choices you may have? Well, that's actually, if the set of x equal to n, you sample rate and both, roughly you are taking the set of S is roughly this much, right? On expectation, this much. Roughly how many such random sample you may have is just n choose rho times n. Does that make sense? Right? you may have this many different random samples that satisfy this condition. You follow me? And that's essentially the set tau in our problem setup. Okay, this is essentially our yeah.
Would it be row and choose n, or am I defining these the other way around?
It's n choose row times n, right?
Okay, maybe I'm confused. I was
Yeah,
thinking maybe
it's
the
n
other way
choose
around.
row times like if n is 100, if something with 5, so it's 100 choose 5.
Is s bigger than nx?
S is a set, right? The size of S is row times n.
So row is smaller than 1?
Row is between 0 and 1.
Oh, okay, I missed that.
Row is the sampling rate, right? Must be less than 1. So that's essentially the tau in the problem setup. You follow me? Now, what the problem asking you to do is to estimate the frequency. So I'm going to erase this, okay? What this problem asks you to do is to show how can you estimate the frequency of particular value A if A is from the universe. I define this as the frequency of value A in the set X, which is all the xi that equal to A, and xi is from the set X. So for example, if my x equal to, then my f3x equals to 3, my f5x equal to 2, f7x equal to 1. What about f2x? Well, that's equal to 0. Do you follow me? All of you? Yeah? No problem? Okay. So the question is, how can you estimate f(ax) when you do not have x itself? You do not have x itself. This is the same problem as the motivation for building a histogram, right? If you have access to the original table, the entire table, if you are willing to pay that cost, linear scan the table or store the entire table, yes, you can estimate the frequency very accurately. But then you need to pay a linear cost, which is to scan x or store x. So the question here is, can we estimate this without actually paying a linear cost? X could be US population, 300 million, or 400 million. So instead of scanning this linearly, can we build an estimator? This is an estimator for this, such that this is a good estimation of f(ax) without looking at x anymore, without looking at x anymore. Okay, that's a challenge. Without looking at 300 million people in US, I can still estimate the average GPA of all US citizens. How do you do that? Okay, so that's essentially what we're doing here, right? You follow me? So first of all, I need to define, what do I mean by a good estimation? What's a good estimation? What's a good estimation? So for any estimation, in order for it to be a good estimation, a typical notion of good estimation is to say this is an unbiased estimator. Unbiased estimator. So to understand what's an unbiased estimator, you really need to understand what's a random variable, right? What's a random variable? What's a random variable? Random variable. A random variable, I can set a random variable like y. Let's say in particular we look at the discrete random variable. There are continuous random variable and discrete random variable. Let's look at discrete random variable. Discrete random variable says you have essentially it's a distribution with a set of values and probabilities. Let's say, okay, let's take value 1 with probability half, take value 3 with probability 2 minus 3, and take value 3 with probability 1, 2. Now this form of a distribution, why? Because the summation of probability equals 1. So it's a proper distribution, PDF. Probability density distribution, right? So for this random variable, what's the expectation of y? Or normally written as this. Y bar is essentially right? All the possible values multiply the corresponding probability sum up. So this particular case is just whatever that value is. That's the expectation, okay? That's the expectation. So with that being understood, once you understood that, you come back here. This is a random variable. It's an estimation, right? So it's not always a fixed value. So it's a random value that I may output to you. In order for this to be a good estimation, this has to be the expectation of this need to equal to FAX. When this is true, we say this is a good estimator. This is a good estimator. You follow me? Next, how do we construct this? How do we construct this? The construction in the problem setup is that I'm going to construct this using it's a random choice. It's a random choice over this. I have this many choice of random samples. I choose one of the random sample from this set. But each random sample is a set as well, by the way. So I randomly choose one set. And I look at what? I look at so the random choice is for this. And I look at how many I simply look at this. How many elements in the sample, in the random sample, equal to the value of A, but then I scale back with probability rho. Then I claim this is a good estimator, meaning the expectation of this equal to this. You have to know that this obviously is a random variable, right? Because it's possible some of these random samples may not have a value A in the X at all. X may have, let's say, 10 A values, but none of them is selected into this random sample. But in another random sample, maybe all A values are selected into that random sample. Does that make sense? What's the probability for each of this random sample to be generated? Well, it's independent to each other, so the total probability is 1, so each one of them is just 1. So the probability that S equal to Si is simply equal to this. That the random choice you make equal to any one of them is simply a uniform distribution. You follow me? Yes? That means that what are the possible value of this? What are the possible value of this? Our possible value of this. In the worst case, it could be 0. No A value is selected. Right? In the best case, equal to what? The max value can only be this. You cannot be more than this. Because that's how many A's you have in X to begin with. You cannot be more than that. You are taking a random sample of it. But they distribute anywhere from there to there. That's why this is a random variable with this probability, just like this. So maybe 0, maybe 1, maybe all the way to FAX. And each one of them has a probability of n rho, n choose rho over n. That's our setup. Do you follow me? Okay? So that's essentially the problem setup. I haven't started on the proof itself yet. So you need to understand all this in order to prove, right? So you need to understand what the problem setup is talking about. Any question on this? Yes.
So, I understand the probability of S there, but with the number of S,
With number of A.
yeah, like the sampling, does it matter like how big the sample set can be?
Oh, each of them, the size of each of them is roughly the same, which is rho times n. Because you are taking a random sample, right? With probability of rho out of a set of size n. So each of them is roughly equal size. But they differ in what elements in it. Does that make sense?
Yeah.
Okay. And because of the second fact, which is they differ in what elements they have selected into the sample, this value will change when you change your random choice. In the worst case, it could be 0. None of the A value is selected, unless what? Unless in the extreme case, unless in that case, 0 is not a possible offer. In that case, actually, in that case, it's extreme case, right? All of these are the same. No matter how you select, you get rho times n A values in it. Right? But let's do not consider this extreme case. So typically, this value will take either some value, maybe 0, but maximum value is just it. You cannot be more than this, obviously. Yes or no? So far so good? Okay. Alright. So what I want you to prove is that this estimator here, which is 1 over rho times number of A values in the sample set, given the random choice is this, choose one of the random sample. This, on expectation, must equal to f(ax). That's what I want you to prove. You follow me? If you think about it, this seems like not so easy to prove, right? Because if you want to prove this by definition, you have to calculate, if you consider this as your y, as the random variable y, you have to calculate the expectation of y. How do you calculate that? Well, the value of y, this is y1, y2, until y whatever, n choose rho times n. For each of the possible value of y, I multiply their corresponding probability, sum up together, and check whether that equals to this or not. But that's really hard to do, right? First of all, you have this many values to consider. Secondly, it's hard for you to estimate what each specific value of y is. You have to carefully calculate, lay out what each random sample looks like, and go from there, count. From the A is there and do that. Impossible. You cannot prove like that. You know what I mean? So this actually sounds like a trivial thing to claim, but it's not so easy to prove. It's not so easy to prove. Next, I will show you how to prove this. Okay? I will show you how to prove this. So far, so good, right? In order to understand the proof, you have to understand at least what the problem is I'm asking you to prove. Okay? So what I'm doing is to try to help you understand what the problem is saying. Right? What is the random choice? What is expectation here? Right? Okay. So how do we prove this? How do we prove this? So I'm gonna pull up the proof. Then I will go through this proof with you together. Now, what I will do is, so what's given? You are given a set X, you are given a universe U, you are given a sampling width rho. These are given, right? So I define this notion of XA, which is essentially the subset of X. Obviously, XA is a subset of X. Subset of X is those elements in X with value equal to n. I define this. I just define this, right? There's nothing wrong with it. I just define it. No trick here. And also with this definition, I also let the set, assuming the set of this is M, obviously by definition, f(a(x) essentially is just the value of M. Okay? Do you follow me? Now what I will do is xa, if x is x1, x2 until xn elements, I will index xa, the element in x, using the same index here, but obviously I cannot index them as this. Because what you are saying is this is the first n elements from x. Obviously that's not true in the general case. So you cannot use this as your index here anymore. So what you will say is, okay, I will index them using another variable where any li is a value from 1 to n. That's fine, right? So for example, I select this, I select this, I select this. If I do that, then my L1 here is essentially equal to 2. Do you follow me? I just use another set of variables to denote those ones with value equal to A from the original set X. But the total set is still M, 1 to n. So far so good? Yes? Okay, once you understand, this is the most important part. Okay. Once you understand this, what I will do next is I define what I call indicator variable. An indicator variable is either 1 or 0. Okay? I define my indicator variable as ILI for I from 1 to n. Basically, for each of this, I define an indicator variable that equal to 1 or 0. Equal to 1 if and only if xli is sampled into a random sample S is equal to 0 otherwise. It's just to indicate whether you are selected into the sample or not. It's an indicator variable. It takes value either 0 or 1. By the way, note that this obviously is a random variable. Why? Because it changes value when you choose a different random sample S among this set. Does that make sense? Yeah? Right? The value of this